an event has gone off.
Wow, now something really, really cool is happening. One of my most exciting days as an astronomer ever, really.
And so that's when it, like, wow, this has actually happened.
This was a really incredible discovery that shook the scientific world. Utterly extraordinary.
This was hypothesized 100 years ago, basically.
For a long time, for all those decades, we hadn't detected them.
And it took us 100 years for technology to get to the point where we can measure them.
Something's just come along, something new and unexpected, which has just changed the whole landscape almost overnight.
We get this amazing look into the universe that we never had before.
The information content, of course, of the universe is just absolutely infinite.
So understanding these events definitely will play a key role in understanding why our universe, looks the way it looks today and where we came from.
It's good to remember that when we take a typical telescope and we stare somewhere, we're staring at an incredibly tiny patch of the sky. And then, of course, we point the telescope somewhere else. And so what we've really got is a universe that we've stuck little pins into temporarily. Everything else we don't know about. What we're moving towards is trying to study and observe the whole universe all the time so that we can have a movie of every point on the sky.
South Africa is currently in a very privileged position where we host a number of world-class facilities, such as those here at the South African Astronomical Observatories, including the Southern African Large Telescope, which is a 10-meter class optical telescope, and it's one of the biggest telescopes in the world.
We began a project in 2020 called the Intelligent Observatory with the idea that not only do we operate the telescopes remotely, but furthermore that we actually integrate and hand over some of the human decision-making to a computer.
With technology, astronomy has grown, I want to say exponentially. Things are now possible that has never been possible before.
And that adds a whole layer of flexibility to observations, that you can control things remotely.
Remote operating rooms are ideal for events that can only be observed on a specific night. So if an alert came out and there's something interesting to observe, the observer can request that specific night or that specific hour. Once they're done with their observations, they would just hand it over to the next astronomer that can be sitting from the remote observing room or even from their home in principle.
The engineering and software that has to go into making that possible, it's immense. And I know all of these small telescopes in Sutherland are also now remotely observable. So they have an observing room here in Cape Town where people can just come and observe from here.
That's the first step. The next step is that you won't actually have an observer at all. So you could just pre-program the telescope before the night and just queue an observation, and we'll just complete the queue throughout the night and complete those observations.
Going from a traditional observatory to an intelligent observatory, we have an 80 years old telescope, 1.9 meter in Sutherland. And I mean, that's like ancient technology, like really old school. But that was converted into a remotely observable telescope just last year. So anybody actually from around the world can operate an 80-year-old telescope from their laptop or iPad, from their bedroom, which is quite an achievement.
In the new era of transient discoveries, these are suddenly new events that are discovered, and many of them may be fairly boring sort of variable objects that you don't really care about, and that's where machine learning comes in, and artificial intelligence, where it's able to sift through basically looking at all different parameters for a given transient object, like how fast did it vary, how much brighter did it become, those sort of fundamental things can be used in these machine learning techniques to say, okay, it's got this, and this characteristics. It's probably this type of object.
If you have large field of views, it's difficult for a single person to look at each image and see what is changing in there. So AI and machine learning is a way to figure out which stars in the field are either dimming or brightening.
Because there are literally millions of sources that get observed, and the only way to determine if they are even real before you want to make an automated classification is machine learning.
It's just too voluminous and it's coming in too rapidly. So you need machines to do this, and that's where the huge development through what we call fourth industrial revolution methods come to the fore, because now the computing power that we have available allows us to do things that we would never have dreamt of before.
Artificial intelligence, which relates to the fourth industrial revolution of how a new way of how you put different themes together in a much more holistic way to answer questions. It really is in its infancy.
We don't really have true artificial intelligence yet in astronomy. What we have are algorithms that can learn from patterns and can adapt to what they see. And I think the next phase of what is generally called artificial intelligence will be the synthesis of human astronomers with artificial intelligent machines.
These type of machine learning algorithms that have been developed can look at massive data sets, and they can do the sort of thing that often scientists and astronomers do, is sort of pattern recognition or comparing something you have just seen with something you know.
In some way, you have to train these telescopes to be able to identify stuff on their own and also be able to react on their own. And so we have a big software team writing software in order to do that. And hopefully in the future, those algorithms become more intelligent, up to the point where they become some sort of artificial intelligence and they can make decisions completely on their own.
So what we really want to do is automate this so that you don't miss very important things. At the end of the day, you have to be at a place where things happen. A telescope observes a new event, and an algorithm, something which gets smarter every time it detects something, it decides whether this is interesting and important or not. And if it is, it decides whether a small telescope is needed now or a large telescope is needed. Are we needing imaging? Are we needing spectra? What kind of spectrograph? And it knows the options, and it sends an automatic trigger to that telescope, which then does it without any human intervention. And in principle, you can do this in seconds or even fractions of seconds.
And in that way, we could follow up on thousands of alerts in a year instead of the 1 or 2 we do at the moment.
That's the goal of having like a lean, mean machine of all the 20-odd telescopes in Sutherland all working together in a coordinated, automatic way. Fourth industrial revolution, or kind of the way of doing things where you take multiple aspects in not just in one domain, or you mesh it together, come up with new solutions. Yeah, it's a big topic, and in astronomy you're only dealing with one aspect of it. I mean, I see it as a way forward in doing things more efficiently. It's doing things more intelligently, and hopefully also more human-centeredness if you do it right. Then for society as a large, it's a way to upskill. If you get students, kids involved in this kind of things, they learn very useful skills.
I think astronomy, especially nowadays, has seen a lot of development in our country itself. Human development, people wouldn't have had access. There's certain scholarships now that's being run, that develops students, it develops people.
That's a big part of our both mandate and what we're passionate about.
To foster young career researchers and students.
mean, the universe is huge, right? And we're seeing only very small part of it. And even close by, we have only so much time, we have only so many instruments, so many telescopes to actually assess it all. I mean, a good example, say exoplanets, planets outside of our solar system. We know that there are hundreds of billions of them in our galaxy. We know that they are there, but we don't know anything about them. Imagine, everyone is a planet. Planet has massive amount of parameters, information, and whatnot.
With each new advance in technology, the sensitivity gets better, and that means we can detect less catastrophic events, or we can detect catastrophic events that are coming from further away. So we expand how far we can see in the universe.
When I look at another human, I see their skin, I see their outside. But if I take an X-ray of that person, so look with X-ray eyes, if you will, we can see the inside of that person. Astronomy works exactly the same way. Different modes of messengers carry different information, and we can put all of that together to really try and understand what a star is made of, what is happening inside of the star, how far is a galaxy away, what is happening to that galaxy, we need all of these different bits of information to be able to put a big picture together. Otherwise, we'll never understand it.
It's a different way of looking at the universe, and it's part of something that's become called multi-messenger astronomy. Multi-messenger is actually things that involve information that you get by alternative means. Gravitational waves is one, but a recent one is also the detection of neutrinos. Neutrinos are essentially subatomic particles, and they're detecting neutrinos from violent events. Tying together now the strands of detecting particles, detecting gravitational waves, and correlating it with electromagnetic multi-wavelength astronomy, it's sort of opened a whole new way of looking at the universe and looking at particularly violent phenomena in the universe, like these events that produce gravitational waves.
Gravitational waves were theorized by Albert Einstein about 100 years ago, actually a little bit more. It was 1916.
And I'm sure back in the day, it must have sounded quite absurd. And I think even in recent history, it probably sounded quite absurd.
In very basic terms, gravitational waves are ripples in the fabric of space and time. For example, when you have two masses orbiting around each other, these cause a ripple in the fabric of space and time.
The idea of space-time is that the whole universe is in what we call the space-time. It has 4 dimensions, so 3 spatial dimensions, and we can see those around us, as well as time.
So to use an everyday analogy, you can imagine space as this fabric or this rubber sheet, similar to that in a trampoline. So that when you put something with mass on it, it sort of bends inwards. And the more massive an object is, the bigger the bend.
So within the space-time then, anything that has mass will distort it. So think of yourself standing on a trampoline and it gets distorted. That trampoline is space-time and you are anything within the universe. And gravity itself is formulated by this. Gravity is basically the curvature of space-time.
These are different sorts of phenomena compared to what we astronomers have been using, namely electromagnetic radiation. When a gravitational wave passes by, causes a sort of distortion, stretching and compressing of space itself. So if you can measure very accurately some sort of distance from one object to another, as a gravitational wave goes by, it would do this, and you should be able to detect it.
So when we're talking about the cause of gravitational waves, at least the ones that we've detected so far, the main culprits are black holes and neutron stars.
There are many different types of stars in the universe. Stars like the sun, but there are also stars that are different from the sun. And one of the most important parameters of a star is its mass. So how a star evolves and what it ends up as depends largely on its mass.
So when you have an extremely massive star, as you keep on adding mass, at a certain point, the gravity, the self-gravity of this thing obviously wants to crush it down. And if it's sufficiently dense and sufficiently big, it will end up as a black hole.
And black holes are weird. Mathematically speaking, they are a singularity, which means they have no necessarily physical dimension. There are some definitions we give them to relate it more to densities and so on.
In Einstein's theory of relativity, what that ends up with is as a puncture of space and time. We don't know what happens at the center of a black hole because that is where the curvature is supposed to be infinite, and we theorize that quantum effects must come in there, which may alter the picture. But further out, there's a thing called the event horizon, which is the last place that you could escape from if you were able to travel fast enough. Once you're inside that event horizon, nothing can escape from that. And that's why it's a black hole.
Certain stars, particularly massive stars, at the end of their lifetimes, they become very unstable. They're no longer stable against gravity. The amount of energy they're producing in the core of the star, which balances the gravity, like in our sun, suddenly that source is gone. And so gravity takes over and the star collapses in an instant, causing what's called a supernova. And what can come out of that is actually a very dense object, like a neutron star.
Much more complicated than a black hole is a neutron star. It's much more complicated because it can have a lot more, in principle, a lot more variety. It's got a lot more flexibility. But essentially, a neutron star happens when you have a lot of gravity. The star is getting compressed to a great degree, but not yet enough to make a black hole. And in normal atoms, the atom sort of looks like, crudely, it's got shells with electrons in it. And on the inside, we've got this nucleus, which has got neutrons and protons. But when the pressure gets so much, the electrons effectively get compressed into the nucleus, and the proton and the electrons become neutrons. And so all you're left with are basically neutrons. So it's a very, very strange state of matter in which you have a star essentially made of neutrons only.
A neutron star is an incredibly dense object with a radius of a few kilometers. So it's much smaller than the sun, but it has more mass than the sun.
One of the key things about a neutron star is just how incredibly dense it is. A single teaspoon of a neutron star would weigh the same as Mount Everest. So extremely dense.
They have such extreme gravitational fields. There's no way we can create such a material on Earth. So it's quite an exotic material at the end of the day at such densities. And those are very important to gravitational waves especially.
Funny things happen in very, very close to these compact objects like neutron stars or black holes. And now when they move, when there's a disturbance of that mass or acceleration or rapid movement, that then disturbs that gravitational field. Gravitational waves are essentially ripples of the gravitational field.
Think of two stars orbiting each other. It will basically make ripples in space-time.
As they spiral each other, they lose energy through gravitational waves. The gravitational waves are carrying away energy. And so as the system loses energy, it has to spiral closer and closer.
And they all happily go in orbit forever and ever. They gradually get closer and their periods of orbiting gradually spins up. But over, many millions or even billions of years that this happens.
If you think about throwing a stone into a pond, you can kind of get an intuition for this size stone, I'm going to get this size waves.
At the center, you will have these very dense waves. And then further out, as they lose energy, they will become, less and less intense.
And when you do that for gravity, you realize that the waves are unimaginably small. You have this catastrophic event, and we can detect it only as the barest ripple.
By the time it gets to Earth, it's these minute changes. in, space-time that we are trying to detect.
So if you wanted to detect gravitational waves, how would you go about it? We know that a gravitational wave stretches space and time. But if space gets stretched, then your ruler, if you were trying to measure distances, would get stretched with it. So you wouldn't actually see a change. It would still be 30 centimeters long. Your ruler would still be 30 centimeters long. So how can you see a change in space? Very clever idea scientists came up with. They take a laser beam, they split it into two, and they send it off at right angles, bounce off mirrors, come back, and then those light beams interfere with each other, and you get this pattern of light and dark stripes. Now, if you stretch this direction, this light has to travel further, and when it comes back, it's not in phase anymore with this light. What you'll see is the fringe pattern move, and that is the signal that something has changed the length of one of the arms, in other words, a gravitational wave.
But it's a really tiny effect. If you think of our closest star apart from the sun, so it's Proxima Centauri, 3-4 light years away. So with modern technology, with a rocket, it would take about 40,000 years to get there. So that gives you the idea of a scale. And in that space, when the gravitational wave now comes through, the distance to Proxima Centauri changes by a width of a human hair. That's crazy. It's so tiny. They're so minute. Albert Einstein, in one of his papers, he said that, this is, this is how it works, but nobody will probably ever detect them because they are so minute, so small. But sure enough, 100 years, almost exactly 100 years later, 2015,
that was the first time we managed to actually detect, i.e. measure, gravitational waves.
And this was due to two black holes orbiting around each other and eventually merging.
This LIGO Virgo machine, really ingenious thing, I detected the first gravitational waves. And exactly as Einstein had predicted. And the technology to do that is just fascinating.
And that was really when everyone just sort of, realized that actually this very challenging technology had actually succeeded.
Both physicists and astronomers were having a field day trying to figure out now the theories of stellar evolution and structure, and how do you get that kind of black holes, because now you essentially saw them via a gravitational wave event.
But unfortunately, black holes don't emit electromagnetic radiation, so they don't emit light. So we didn't see any light from these.
Ever since the discovery in 2015, astronomers were then sort of really hoping to find an event which would potentially produce an electromagnetic signal.
I was doing an observing week at SALT, and then we started getting these first rumors, actually. I think it was one of the other guys in the hostel staying there. Oh, did you? I got a SMS from the LIGO. There was a gravitational wave event again, and a couple of others of us. Oh, okay, cool. But then somebody said, "Hey, did you know that they found a optical counterpart?"
2017, the 17th of August, was the first time ever that we detected a electromagnetic counterpart from one of these gravitational wave events. Two dense objects spiraling in, and eventually, as they get closer in, they're moving faster and faster, and eventually they coalesce.
So the thing that was different in 2017 was the existence of an afterglow. The telescopes could look at, see the smoking gun of this event, this slow decline after the merger that could be followed by telescopes all over the world. And each telescope brought a different piece of the puzzle to understand what was going on with the physics.
There's a lot of physics involved of what happens when these extremely exotic objects collide, and what happens on a physics level. It is such an intense high energy event, that it's been great to be able to observe that and learn from that.
And South Africa was, of course, involved in the multi-wavelength observations that happened with this merger. This is a great demonstration of multi-messenger astronomy, where one instrument detects a signal and then they send out information to other facilities across the world.
That was really important in bringing now the electromagnetic radiation and the gravitational waves together. So for that 2 years since that monumental discovery of gravitational waves, this was a time when the first time we could see, using electromagnetic radiation, what caused the gravitational wave. And the way I like to describe it is that for those few years, we were kind of listening to the universe, we were hearing. And now for the first time we saw who was speaking, putting together those two senses. That was really the significance of the 2017 events.
There's a certain amount of material that's ejected at very high velocity, actually, sort of fractions of the speed of light, 10% or 20% the speed of light. So what you get is this enormous explosion, which is not symmetrical. It's not like a uniform explosion. Some material goes out in the disk of the binary, and other material goes out along the poles of the binary system.
We were right in the thick of it in getting the first spectrum with SALT, which we're still very proud of. You need an observation which doesn't only take an image, but breaks that light into a spectrum, kind of a rainbow-like thing, but just in much more detail, which would then tell you what the object is. And we rushed like crazy that day to kind of stop everything else and put all the focus in getting a very difficult observation, because it was visible only right in the evening and then it would set. From the shape of that spread out light, you can tell, first of all, how far it is, and you could pin it that it definitely happened in that galaxy 130 million light years away, and you could see the light. It's a massive explosion, so for a fraction of a second in energy outshone the whole visible universe. Just massively energetic, absolutely exciting, and knowing that there were 70 observatories in the world at the same time trying to do the same thing. Oh, that was amazing.
Gravitational waves are a direct probe to gravity and to mass, and that has never been possible. So it brings a whole new dimension that is mostly unexplored.
We can essentially peer into the inner structures of stars, of supernovae, things like this, anything where gravity is playing a part.
So understanding these events definitely will play a key role in understanding why our universe, looks the way it looks today and where we came from.
Scientific breakthroughs or scientific predictions require a long time sometimes with technology advancing. For all those decades, we hadn't detected them until we were in a position to use our technology.
There's been subsequent discoveries of binary neutron stars, and even neutron star black hole binaries that are emerging. Means that there's a whole new sort of population of objects that have not been studied, that really we're just sort of learning about these.
Once we have the afterglow, you can imagine that now there's all kinds of elements, and there was a lot of pressures and there are high temperatures involved. These explosive events, you will see the formation of heavier elements like gold, like lead.
And now we had this explosion, we had a spectrum, and over the days that spectrum changed, and you could tell that, essentially, it's not quite this simple, but essentially you could tell that, gold, palladium, platinum, new elements were created in front of our eyes.
That's where these elements come from, literally stardust.
Incidentally, the papers then later who analyzed this whole thing, they say that about 1 Earth's mass of gold was created in this explosion as well, which probably would wreck the stock market, right? The gold in my, wedding ring over here was created in explosions like this, just closer to Earth. And then eventually that material came to the proto-Earth and it was here and somebody dug it up and made a ring out of it. And it's just amazing.
South Africa was part of a really worldwide effort to image this afterglow in as many different ways as possible. So it was a beautiful example of international collaboration about the world working together for the benefit of humanity. The amazing thing about gravitational waves is that you can hide, you cannot emit light, you cannot emit radio waves, but you cannot avoid emitting gravitational waves. So it's the last place the universe can hide. When an event like this happens, you have a very short amount of time. Ensuring that the telescopes got to the right place, the right direction as soon as possible is obviously something that requires excellent communication, collaboration, and sharing of data. So this is really an example of astronomy enabled by all of the advances in data analysis and communications that we characterize the 21st century by.
I think the discovery of gravitational waves just demonstrates that when you open in a new frontier and you use new technology, there's a lot of discoveries to be made.
These transient events haven't just started happening recently, they've been happening all the time. It's just we've been blind to them. We just didn't have the technology to be able to capture all these events in one go.
This event, 2017, we started developing here at SAAO the Intelligent Observatory project of automating things, not operating single telescopes which do separate things, but working them together. The key is to process a lot of new data very quickly.
Astronomy started by observing single objects, looking at one star, then one galaxy. And there it was about patience and dedication and time, often decades to watch individual objects. A branch of astronomy naturally rose where it was asking, well, what about the whole universe? Einstein did a lot of work on cosmology, as it's called, the study of the whole universe. And there, one's not interested in individual objects, one's interested in the whole collection of objects. Like, how many galaxies are there on average? What's going to happen to the universe? Is the universe going to expand forever? And so that comes down to understanding the average properties of the universe. And if you want to talk about averages, you need lots of data. Astronomy was a big data subject before big data became popular.
These images are just becoming larger and larger. So in a single frame, you're just capturing many, many more stars than what you did 10 years ago. And so in the past, an image might have 10 or 15 stars. Now images are having thousands or 10,000 stars. And it's just impossible for a single person to be analyzing that by hand. You need these algorithms to be able to extract the photometry or the spectra from each individual star.
Astronomy is one of the fields of science that relies heavily on data availability and data capture.
They're all extending how much of the sky we can watch, how deep we can see.
So we need to develop tools to process that data and save it in a way that withstands time as well, that then the next generations actually have that. We don't want to lose it.
There is so much data. There is now too much data almost, that everything needs to be captured in a very structured way, and there needs to be very efficient algorithms written to identify different sources and to be able to analyze it in a reasonable amount of time.
If you take examples of radio astronomy, like Meerkat, raw data is coming in at terabytes per second, right? That has to be processed on site at Carnarvon. We call it pipeline reduced, where the raw data goes through some software which does calibrations, it corrects for certain things, and the data is available to the astronomer who asked for the observations the following day.
There are all-sky surveys that looks at thousands of sources per night. It's a whole new ballgame.
The biggest data sets are wide imaging data, where you're looking at hundreds of thousands or millions of objects per frame.
And you can't deal with that kind of data quantity or the frequency of new things happening in the traditional waves. You need machine learning, intelligent software to make the decisions, and then propagate that to all the telescopes and instruments that we have to make smart decisions of what follow-up needs to be done.
At its peak, the SKA will produce around an exabyte of data per day, so be producing around 1 million terabytes every night. You can go away and calculate, well, how much data did the whole of humanity produce before the year 2000? And it's of order 10 exabytes. So SKA will produce in a week roughly the same amount of data as the whole of humanity produced before the year 2000. Typically, we're looking for incredibly small signals. In an exabyte of data, there might only be 10 bytes of useful information. And for that, you need incredible computing power, and you need very, very clever algorithms, because humans can't look at that data. We already past the point where humans can look at all the data.
Having software which analyzes the data for you much quicker than you can do yourself, and visualizes things as well, so that it's easier to understand.
And that's why in South Africa this initiative began several years ago, of forming a consortium of people who were interested in what's called data-intensive astronomy. So there's an institute called IDEA, the Inter-University Data-Intensive Astronomy Institute,
which is a collaboration of several South African institutes and universities. They help the rest of the research community and astronomy community to deal with massive amounts of data, big data, and facilitate storage and data reduction and what to do with it and get the most out of it.
Allowing universities to work together to develop the sort of facilities that can support this data-intensive science.
One of the key things about science is that we have to be able to handle uncertainty in a very structured, rigorous way. If you're looking for a needle in a haystack, and there's one needle and 1 billion pieces of hay, then even if only 1 in 1 million pieces of hay look like a needle, you're going to get 1,000 fake needles and only one real needle. So you have to be very, very rigorous about knowing the difference between something that looks like a needle and something that really is a needle. This is the essence of science and doing good science. And so, of course, when the COVID pandemic hit, scientists, physicists, astronomers were very well placed to help epidemiologists, traditional people who study the spread of disease, exactly because COVID involves so much uncertainty.
Astronomers are good at quickly analyzing large data sets. That was critical during the COVID thing, is to, try and get predictive models out as quickly as possible out of the data.
So we're not interested in, we found 10,000 cases. We're interested in how many new people were infected today. And that's a very difficult problem, but it's exactly the kind of problem we've been facing in astronomy for 100 years. When we look out at the sky, we see a star explode. We're not interested in the fact that there was one that exploded. What we were interested in is how many stars exploded yesterday in the universe. So we were able to use many of the techniques that we've developed for dealing with this kind of uncertainty in our forecasts for COVID modeling in South Africa.
If we're going to do science and advanced science, then sharing collaboration is the only way forward.
Astronomy nowadays is fully global. To really pursue the most interesting, cutting-edge scientific questions, or the big burning questions that we still don't understand of the universe, the equipment needed is actually quite expensive. So you need collaborations to plan for them, to build them, and to operate them. But then in addition, you need collaboration also for just the sky coverage, especially in this field of things changing in the sky.
What we would really like is to be able to study objects 24 hours a day, 7 days a week. But of course, because the Earth rotates, any single observatory can't look at an object all the time. There's a kind of a handing off of the baton often, where we can pick up observations of targets of interest, and then we hand off again to observatories somewhere else in the world.
So it is important that we have a global network of multi-wavelength telescopes so that we can all work together to discover things of the universe.
In the future, it would be great if all observatories were interconnected, and if some very exciting transient event happened, the global community could just decide how to observe this from all over the world. Have no gap in the data because we will all be in different time zones. We can just tackle this problem from all the angles possible and learn as much about this transient event as we can.
We know there are things out there that we're going to discover. So I'm really excited about that prospect of finding things that no one expected.
In the fourth industrial revolution, where we are now with our capabilities, technologically wise, what we're going to find with that is still going to be mind-blowing. I think we'll be able to bring together observational astronomy as well as theoretical, astrophysics in a way that we've never been able to do before. And with that, really, get to understand the universe a lot better.
Any civilized society does more than just feed and clothe ourselves, We do what they call blue sky science, doing science just for curiosity.
Sometimes they have quite practical spin-offs. The World Wide Web came from CERN, from physicists just wanting a more efficient way to deal with some of their file systems and all that.
One big example that I'm sure nobody can imagine their life without nowadays is Wi-Fi. Where did that come from? Oh, that came from radio astronomy.
Your mobile phone camera uses technology that was developed for optical observatories and telescopes like Sutherland.
Infrared cameras, which you go to airport and your temperature is automatically screened, who started using that technology and developed that technology to take infrared images of the universe because we wanted something to compare with the optical images to understand how stars work and how star formation work.
If you didn't allow for Einstein's theory of relativity, the one that predicted gravitational waves, your GPS would be off by about 1 kilometer every day. Einstein never thought it would have technological applications. There are countless examples of these amazing technological breakthroughs that take 10 or 20 years to come through to society, but when they come through, are completely revolutionary.
The discovery space, the potential for finding or understanding things better than we've ever done before, that's the potential, that's the future of astronomy.
And I think astronomy is like that. It leads to wonderful technological innovations, but more profoundly, I think it really is about our place in the universe. It is this beautiful subject that belongs to everybody. Each time we make a breakthrough in astronomy, we get a new understanding of our place in the universe.